We've been studying linear constant coefficient DEs, not homogeneous in general, and in the case of rest initial conditions, we can study this kind of problem with the Laplace transform. So if we take the Laplace transform of both sides of this DE, what will end up because of these rest conditions is that we'll just get some polynomial that multiplies the transformed function that we're looking for. If we divide through, remember that we gave this reciprocal 1 over the polynomial, we gave it a new name called the transfer function. Now the transfer function ends up encoding all of the information about the left-hand side of the differential equation, the differential operator. In the case of rest initial conditions, all we have is the following for the transformed solution. It's a product of these two functions, the transfer function and the transformed right-hand side. So it makes it really, really easy for us to swap out different right-hand sides and come up with solutions. And in particular, why do we care about the transfer function? It's because the transfer function allows us to get the Green's function for our problem very easily. So remember that if you take the inverse of the transfer function and then you shift the result, it will end up producing the Green's function for our problem. And not only that, it will tell us something that the Green's function ends up being a shifted function like this. So that means then that our particular solution, or actually the solution to this IVP, has the form of a convolution. And it's really nice because the Green's function encodes all the information about the left-hand side, the right-hand side directly plops in like this, and we're done. So it is of key importance for us to find the transfer function. So then the idea here is, in order to make our lives easy, so to make it easy to find the transfer function, I would really want to know, is there some sort of function, and I'm going to call it delta of t, so that when I take its Laplace transform, I get a 1. And you might say, well, why would you want to do that? And I'll show you here. Because if I have the same setup where I have my differential equation and I have this mystery function, and again with rest initial conditions, if I take the Laplace transform of both sides, the fact that this thing has a Laplace transform of 1 basically means I'm going to get my transfer function out very, very easily. And so I'll end up with this polynomial, the thing that I'm looking for, and y of s in this particular case is going to be 1 over p of s, which is just the transfer function. So it's kind of a convenience. It's a convenience here because it will just simplify the steps. There's no need to worry about a specific right-hand side, because if I just pick this right-hand side, they'll always give me a 1 when I take its transfer. So what function does this? Is there a function that does this? And it's going to turn out that intuitively we can come up with a result, but it won't really be a function. And I'll explain that to you in a sec. Right? And so here's the idea. We're going to define a box. So we're going to define a box function. And the box function we're going to define like this. It's a piecewise function. We will have the value of 1 over epsilon between 0 and epsilon, and it will be 0 otherwise. So if I were to graph this, it would look like I say, we'll have a 0, a hole here, we'll be at some height of epsilon, and again, a discontinuous change right there, and we'll go back to 0. So this is a picture of the delta that I'm calling here. And this is the time. So the idea now is that we are eventually interested in integrals, right? We're interested in the Laplace transform. And because the Laplace transform is an integral, sorry about that, because the Laplace transform is an integral, what we want to know is how does this thing behave inside of an integral? So how does this behave when I integrate? And I want to integrate everywhere. And so let's take a look, right? So I want to study how this thing is going to behave if I integrate it from 0 to infinity. Because it's 0 everywhere except for that small range, we can say that, okay, this will be an integral from 0 to epsilon f of t 1 over epsilon dt. Now we're going to get a little bit hand-wavy here. We're going to get a little bit intuitive. But the point here is that for epsilon being very small, f of t is approximately f of 0, which is a constant, right? Over this very small width here, epsilon, this function may not change its height very much. We're going to assume that that's the case. We've got a nice continuous function on perhaps even discontinuous, but over that small interval, we're hoping it doesn't change very much. And then the idea is, okay, if that's approximately f of 0, it's a constant. I'm going to take it out of the integral. So it'll be f of 0, integral 0 to epsilon 1 over epsilon dt. This is a box. And so we're essentially saying, what's the area of this box underneath here? It's going to have a height of 1 over epsilon times a width of epsilon. So this is just going to be 1. And so what ends up happening is we pull out the value of the function at one point. 0 to infinity, f of t. If we were to integrate this delta, it would approximately give us the value of this function at 0. So we're trying to build some sort of magical delta that will pull out specific values. This is called a sifting property. It just pulls out the one value that we were interested in. Now, as epsilon goes to 0, this becomes a better approximation. And so what we're going to say is that as epsilon goes to 0, we'll say that this thing equals f of 0. Now, we could do this more generally. So in general, we could define our box like this, delta of t minus c, and we'll define it as a piecewise function again here. We'll say it's 1 over epsilon if t is between c and c plus epsilon. And then we'll say it's 0 otherwise. So this is a box that's just been moved over to c. It'll be discontinuous. It'll be 0 up to that point, 1 over epsilon, just there, and then it drops down again. So that'll be c plus epsilon. Now, if we were to do this in the more general case, if we were to then take the integral of this delta t minus c, we would say that it would equal just f of c as the size of this epsilon went to 0. Now, the key thing here, there's a logical problem here. This delta isn't a function. There is no function that can do this. And you say, well, what's going on, right? Because in the limit that epsilon goes to 0, our function is essentially 0 everywhere, but has a non-zero integral. Right? That's a problem. And in fact, these aren't functions. So intuitively, what had happened historically is somebody named Dirac came up with this idea, and said, hey, I'm going to create this function that behaves this way. It wasn't really a function. And then he said, yep, it works. He solved a lot of problems with it and then threw it to mathematicians to say, you figure out why this works. But it turns out he was right. So this is something called a distribution. So it's a entity that only has meaning when you integrate it. But that's a different story for down the line. We are going to work with this. So we're going to call this thing the Dirac delta function. Now, it's not really a function. And remember, we are shrinking this epsilon to 0. What happens is that in my piecewise function, remember, I am going from c to c plus epsilon. And it's 0 otherwise. As this epsilon goes to 0, what you're finding is that the box is going to get taller and taller and more narrow. So as you take this c plus epsilon and you shrink the epsilon this way, the box is going to get more and more narrow. And so what you end up with is really an infinite spike. Because as epsilon goes to 0, the height of the box goes really high, but the width of the box goes to 0. So it's essentially an infinite spike. Sometimes we call this an impulse. And an impulse is a sudden change. Now, physics people like to use impulse for a sudden change in momentum. But generally, we are going to use the delta function as a sudden spike. Now, sometimes engineers, physics people like to draw the delta function with just a vertical line. Why do we care? It's used to model what we'll call a sharp blow to a system. And I'll talk about that in just a moment. But back to the point. So now, if we talk about the Laplace transform of this delta function, what we are saying is let's integrate from 0 to infinity. We're going to take e to the minus st delta of t minus c dt. That's the definition of a delta function. We're going to use the sifting property. And when we do that, it just pulls out the value of this function at that location. That was the whole point. That was the reason why this function was defined and built the way it was. So we are going to essentially pull out the value of this thing at t equals c. So this will end up being e to the minus sc. In general, the Laplace transform of the delta shifted to c is e to the minus sc. And so the whole point of the story here was, if I just take the Laplace transform of the delta centered at 0, I'll get e to the minus s times 0, which in fact is a 1. And that was the whole point behind what I wanted to do. I wanted to figure out a magical, air quotes, function, so that when I took its Laplace transform, I got a 1, because that's going to help me find the transfer function. So before I get into more details about using it in the context of transfer function, I'm going to use it to talk about some basic system modeling. I'm going to talk about using this to work on models. So if I were to say to you, okay, 2y double prime plus y prime plus 2 is delta of t minus 5, and then I'm going to take these conditions. Y of 0 equals y prime of 0 is equal to 0, rest initial conditions. This thing right here is a model for, again, a sharp blow to the system at time equals 5. So right at this point, there is 0 unless t4. So this right-hand side has a value of 0 for time not equal to 5, but then it's infinite for t equals 5. Now again, that's not a function. A function can't have an infinite value. So the Laplace transform, because it's based on integration, it can handle this. Our standard methods can't. What you should be thinking about here is a mass on a spring, and then you come by and hit it with a hammer. Boom, right at a sharp time. And you do it very quickly. That is the use of this delta on one practical level. So if we were to take the Laplace transform of this equation, what's nice here is that we've defined or built the delta function so that we can actually take its Laplace transform. That is the only way that the delta function has meaning. If I go ahead and remember that I have rest initial conditions, everything on the left-hand side will turn to this. The Laplace transform of a delta is e to the minus s wherever the center is. That's the one thing about there. The rest initial conditions mean that all of these y of 0, y prime of 0 are 0. So that's what's left on this side. Remember that we now have this polynomial on the one side, and that's going to determine our transfer function. 1 over 2s squared plus s plus 2 e to the minus 5s. This thing here is the transfer function, and that encodes everything about the right-hand side. Remember, the zeros of the bottom, the poles, are going to tell us everything about the solution. We want the inverse transform of this expression. So we want the inverse transform of e to the minus 5s over 2s squared plus s plus 2. Whenever we have an exponential in frequency space, we need to use the shifting theorems. Remember, the shifting theorems tell us that exponentials in one space end up being t shifts. And so what's going to happen here is that this is simply going to be the inverse transform of 2s squared plus s plus 2. That answer is a function of t, but it's going to be shifted to t minus 5, and we're going to multiply it by the unit step, t minus 5. So our job then becomes, what's the Laplace transform of this thing? Well, you can handle this thing by talking about completing the square. So I'm going to factor out a half. I'll have 1 over s squared plus a half s plus 1. And we can complete the square. We'll have an s squared, 1 half s. And then we'll put the 1 here. The b is a half. B over 2 is 1/4. B over 2 squared is 1/16. So if I put in a 1/16 and take out a 1/16, the purpose of doing this is to write it as a shift. And it will always be a shift with whatever the value of b over 2 is. So it'll be s plus 1/4 squared plus 15 over 16. So I'll have a 1/2 inverse Laplace transform of 1 over s plus 1/4 squared 15 over 16. And in order to be able to invert this properly, this is very, very close to the inverse transform of a sine function. But I need a root 15 over 4 up top in order to make the transform work. I can't just put a root 15 over 4 on the top. That means I have to put one on the bottom out front. So I'll get a 4 over root 15. Now I need to use the S shifting theorem. So this will give me a 2 over root 15, Laplace inverse of root 15 over 4, s plus 1/4. I should say I'm shifting it, s squared plus 15 over 16. And remember, when we use this property, what's going to happen is that we will gain an exponential in t space. And this is now going to provide me with an exponential of t to the minus 1/4, just like that. And finally, I'll get 2 over root 15. the sine of root 15 over 4 t e to the minus t over 4. So that was a bit of a whirlwind, but we're not done. Remember, way back when, what we are trying to do is figure out this thing that we've just spent a lot of time on, and then it's going to have to be shifted and unit stepped. So the idea of the story now is that our solution is going to be 2 over root 15 e to the minus t over 4 sine of root 15 over 4t. That's all going to be shifted to t minus 5 and then multiplied by a unit step, t minus 5. So the solution here is 2 over root 15 e to the minus t minus 5 over 4 sine root 15 over 4 t minus 5. All of this multiplied by unit step. So yeah, coming up with the formula is great, but it's useless unless you know what it's trying to tell you to do. You could imagine that a sine function oscillates up and down. This exponential function decreases the amplitude, and the unit step turns it on. And that's really what we were after. Remember that this system was at rest until time 5. And at time 5, what's happening is that I've struck it with a blow. And then it will start to oscillate, but it will have this decreasing envelope due to the exponential. And that's exactly what I expect to see. I expect to see a sharp impulse at time 5, and then this underdamped behavior afterward. In that sense, the delta function is great as a physical model. We're going to look at in the next video how it's useful for mathematics in the Green's function.